Today we will prove Tietze extension theorem, which is a very important theorem in topology. This tells us that any real valued continuous function on a closed subset of a normal space can be extended to the entire space. It is named after Austrian mathematician Hendrik Franz Friedrich Tietze. In this photo, he is in the right. Tietze extension theorem states that a topological space Xt is normal if and only for any closed set f in X for every real valued continuous function f from closed subset f to closed interval ab, there exists a real valued continuous function g from whole space X to closed interval ab such that g is a continuous extension of f. That is, both g and f agree on closed set f. That is, f is a restriction of g to set f. Let us prove this theorem. Let for a closed set f in X and for every real valued continuous function f from closed set f to closed interval ab, there be a real valued continuous function g from x to closed interval ab such that g is a continuous extension of f over x, that is, g restricted to set f is equal to continuous function f. We have to show that xt is normal. Let A and B be two disjoint closed subsets of X. As we want to show that space is normal, then we need two disjoint closed sets. So here we are taking A and B disjoint closed sets in X. We define a function f from A union B to closed interval AB such that f of x is equal to A if x belongs to A and f of x is equal to B if x belongs to B. Then for any closed subset H of closed interval AB, inverse image of H under F is equal to A if A belongs to H and B doesn't belong to H, because image of every element of set A is small a. So if we take inverse image of any set which contains A, then that will be equal to A. And similarly, if B belongs to H but A doesn't belong to H, then inverse image of H under F is B. And if A and B both are belonging to H, and if we take an inverse image of H, then that will be equal to A union B. And if A doesn't belong to H and B doesn't belong to H, then inverse image is phi. Why? Because there does not exist any element in A union B whose image is other than A and B. And so here we have phi. As A and B are T closed, and if we take intersection of A and B with A union B, then that will be a closed set in A union B. And when we intersect A with A union B, then we get A, and similarly B intersection A union B is B, and so these are closed set in the subspace A union B. As clearly A union B and phi are closed in A union B, so we have shown that inverse image of any closed set under F is closed in A union B. Hence, F is a continuous function. As A union B is closed in X and f is a function from A union B to close interval AB. So this is a real valued continuous function, and we have assumed that if we have a real valued continuous function from a closed set of X to close interval AB, then there exists an extension of that function. So by hypothesis, there exists a real valued continuous function g from x to close interval a b such that g restricted to a union b is equal to f, the function f, continuous function f, that is g of x is equal to f of x for every x belongs to A union B. And so g of x is equal to small a for every x belongs to A, and g of x is equal to B for every x belongs to B. Because g of x is equal to f of x, and for every x belongs to B, f of x is equal to B. So here we have g of x is equal to B. Hence, by converse of Urysohn's theorem, xt is normal. Conversely, let xt be a normal space, let f be a closed subset of x, and f be a real valued continuous function from closed set f to closed interval -1, 1. For numerical convenience, here we are taking closed interval AB as closed interval -1, 1. Now we define a function f naught from closed set f to closed interval -1, 1 by f naught of x is equal to f of x for every x belongs to f. That means both functions f naught and f are the same. Let g naught is equal to inverse image of closed interval -1 by 3 under f naught, and h naught is inverse image of closed interval 1 by 3 1 under f naught. And as these intervals are closed in -1 1, as these intervals are closed in the usual topological space, these are also closed in the subspace closed interval -1 1, and f naught is continuous, and we know that inverse image of any closed set under a continuous map is closed, and so here g naught and h naught are closed in f. As f itself is closed in x, so g naught and h naught are closed in x. Also, g naught intersection h naught is equal to f naught inverse closed interval -1 by 3 intersection f naught inverse closed interval 1 by 3 1, and that will be equal to f naught inverse of closed interval -1 by 3 intersection closed interval 1 by 3 1, and this is equal to 5. As G naught and H naught are disjoint closed sets in X and X is normal, so by Urysohn's lemma, there exists a continuous function G naught from whole space X to closed interval -1 by 3, 1 by 3. Here we are taking closed interval as -1 by 3 and 1 by 3, such that G naught of set G naught is equal to -1 by 3, and g naught of set h naught is equal to 1 by 3. We are taking images of g naught as the left end point of the interval, that is -1 by 3, and images of elements of h naught under g naught is equal to the right end point of the closed interval, that is 1 by 3. We next define a map f1 from closed set f to closed interval -2 by 3, 2 by 3 by setting f1 of x is equal to f naught x minus g naught x for every x in f. As f naught and g naught are continuous functions, and they are real valued continuous functions, their difference is a real valued continuous function. So f1 is a real valued continuous function, and here we can check that the range of f1 is contained in the closed interval -2 by 3, 2 by 3. If we take any point x in g naught, then by definition of the set x g naught, uh, f naught x lies between -1 and minus 1 by 3. And g naught x is equal to minus 1 by 3. And so minus 1 plus 1 by 3 less than or equal to f naught x minus g naught x is less than or equal to minus 1 by 3 plus 1 by 3. That is, we can check f1x lies between minus 2 by 3 and 0. And if we take x in h naught, then f naught x, by definition of h naught, f naught x lies between 1 by 3 and 1. And we know that g naught x is equal to 1 by 3. So f naught x minus g naught x lies between 0 and 2 by 3. That is, f1x lies between 0 and 2 by 3. And so all these images of f1 lies between closed interval minus 2 by 3 and 2 by 3. And if x doesn't belong to g naught and h naught, then f naught x lies between minus 1 by 3, 1 by 3, and g naught x lies between minus 1 by 3 and 1 by 3. So, and that means minus g naught of x lies between minus 1 by 3 and 1 by 3. In this way, we find that f naught x minus g naught x lies between minus 2 by 3 and 2 by 3. That is, f1x lies between minus 2 by 3 and 2 by 3. And so images of elements of f under f1 lies in closed interval minus 2 by 3, 2 by 3. As f naught and g naught are continuous functions, so their linear combination is also a continuous function, that is f1 is continuous. Now let g1 is equal to inverse image of closed interval minus 2 by 3 minus 1 by 3 into 2 by 3 under f1, and h1 is inverse image of closed interval 1 by 3 into 2 by 3, 2 by 3 under f1. Then as before, we can show that both G1 and H1 are closed sets in F, and so they are closed sets in X, and they are disjoint also. So by Urysohn's lemma, there exists a continuous function G1 from whole space X to closed interval minus 1 by 3, 2 by 3 and 1 by 3 into 2 by 3, such that G1 maps to each element of set G1 to minus 1 by 3 into 2 by 3, and G1 image of each element of H1 is 1 by 3 into 2 by 3. We next define a function f2 by setting f2 of x is equal to f1x minus g1x, and f2 is a function from set f to closed interval minus 2 by 3 square, 2 by 3 square. And since this is f2 is a linear combination of continuous functions f naught, g naught and g1, so f2 is clearly a continuous function. We continue this construction by induction. Then for n is equal to 0, 1, 2, 3 up to m minus 1, there exists a continuous function gn from space x to closed interval minus 1 by 3, 2 by 3 whole to the power n, 1 by 3, 2 by 3 whole to the power n. We next define a function fm is from closed set f to closed interval minus 2 by 3 whole to the power m, 2 by 3 whole to the power m. By setting, as before, fmx is equal to f naught x minus summation of gnx, and varies from 0 to m minus 1 for every x belongs to f. Then as fm is a linear combination of continuous functions, so fm is also continuous. We write gm is equal to fm inverse of closed interval minus 2 by 3 whole to the power m minus 1 by 3, 2 by 3 whole to the power m, and hm is equal to fm inverse of closed interval 1 by 3, 2 by 3 whole to the power m, 2 by 3 whole to the power m. We observe that, as we have observed earlier also, gm and hm are disjoint closed subsets of f and so are closed in X. So by Unison's lemma, there exists a continuous function gm from space X to close interval minus 1 by 3 to 2 by 3 whole to the power m, 1 by 3, 2 by 3 whole to the power m, such that Gm maps to each element of set Gm to minus 1 by 3, 2 by 3 whole to the power m, that is the left end point of the interval, and Gm maps to each element of Hm to 1 by 3 into 2 by 3 whole to the power m, that is right end point of the interval. We define a function fm plus 1 from set f to close interval minus 2 by 3 whole to the power m plus 1, 2 by 3 whole to the power m plus 1 by setting fm plus 1 of x is equal to f naught x minus summation gnx n varies from 0 to m for every x belongs to m. Then fm plus 1 is continuous, being linear combination of continuous functions. So this completes the induction. As mod of g and x is less than or equal to 1 by 3, 2 by 3 whole to the power n for every n is equal to 0, 1, 2, 3, and the series in the right hand side, that is summation of n is equal to 0 to infinity 1 by 3, 2 by 3 whole to the power n is equal this sum of this series is 1, that is this series is convergent. So by Weierstrass's M test, the series in the left hand side, that is summation gnx n is equal to 0 to infinity, this series of functions converges uniformly. Let this series converges uniformly to g of x for every x belongs to x. And we know that any series of continuous functions converges uniformly to a continuous function. So g is a continuous function on x. And as mod of g of x is equal to mod of limit m tending to infinity summation n varies from 0 to m g n x, and this is limit m tending to infinity mod of summation g n x n is equal to 0 to m, and because mod is a continuous function, so limit can be taken outside, and this is less than or equal to limit m tending to infinity summation m is equal to 0 to infinity mod of g n x, and this is less than or equal to summation n is equal to 0 to infinity 1 by 3, 2 by 3 whole to the power n, and this sum is 1, and so we can say that g of x varies from minus 1 to 1, and so g is the function from x to close interval minus 1, 1, and this is a continuous function, and this is from x to close interval minus 1 to 1. It remains to show that g is a continuous extension of f naught. We note that mod of fm of x is less than or equal to 2 by 3 whole to the power m. And the sequence, we know that this sequence 2 by 3 whole to the power m converges to 0. So limit fm of x m tending to infinity is equal to 0. As we know that by definition of fm, fm of x is equal to f naught x minus summation gnx n varies from 0 to n minus 1 for every x belongs to f. So if we apply limit m tending to infinity, then left hand side becomes 0, and the series summation gnx n is equal to 0 to m minus 1 will become summation of the series gnx n varies from 0 to infinity, and this we know that this is equal to g of x. So we find that g of x is equal to f naught x for every x belongs to f. And we know that f naught x is nothing but g of x. So we have shown that g of x is equal to f of x for every x belongs to f. That means g is a continuous extension of f. Thank you.